Good evening, everyone. Today, I am going to explain a very important concept in a fluid flow, which is related to the movement of fluid layer and which is classified as laminar and turbulent flow. So, basically, a fluid can be differentiated on the basis of layered movement or haphazard movement. And this categorization is based on the dimensionless number, which is known as Reynolds number, and it is defined as the ratio of inertia force to viscous force. This all detail we are going to see further. So now here we have come to know about viscous force. So we are going to define viscosity. So what is viscosity? It is defined as internal resistance offered by one layer of fluid to the adjacent layer. So suppose there is a fluid flow. This is the fixed surface and fluid is flowing in this direction. So this layer will be in directly contact with this wall. So as the particle which is in contact with this wall, it will come to the rest and gradually its velocity will increase. So this layer will offer a resistance to the adjacent layer, and this resistance is because of the viscosity. The main reason is viscosity, and the main reason for viscosity in case of liquid is molecular bonding or cohesion. Cohesion, it is defined as the intermolecular forces of attraction between the same molecules, and adhesion is from different molecules. Whereas in case of gases, the molecular collision, which is called the molecular momentum transfer, it is the main cause of viscosity. For a static fluid, viscosity is not zero, but it will come into the observation when once the fluid start flowing. Now, viscosity represent easiness of flow, how easy a flow is. So more is the viscosity, more is the resistance, and difficult is the flow. So basic relation we should remember that more viscosity, more resistance. More resistance, difficult to flow. The SI unit of dynamic viscosity is kg per meter second or pascal second. And kinematic viscosity, which is defined as, which is represented by nu and equal to dynamic viscosity divided by density of the fluid, and its unit is meter square per second. Now we will define one of the very important number or ratio, which is the Reynolds number. It is basically a dimensionless number, which is the inertia force by viscous force, and it is mathematically represented at rho VL by nu, where rho is the density of the fluid flow, V is the velocity of flow, L and D is the length and diameter respectively. So in case of plate, we are using flow over a plate length, and in case of flow through pipe, we are using D, which is the diameter of the pipe, and mu is called the coefficient of dynamic viscosity. Sometimes instead of mu, we are given with nu, which is called the kinematic viscosity and defined as dynamic viscosity upon the density of the fluid that is flowing in the pipe or over the plate. For non-circular region or non-circular shape, we use the formula Reynolds number is rho v d effective by nu, where d effective is 4a by p, where a is the area and a cross-sectional area and p is the perimeters. So now we will know about Reynolds number for different type of flow in different condition. So we have air flow and condition and type of flow. So if the flow is in pipe and laminar number is less than 2000, Reynolds number is less than 2000, then it is a laminar flow. If it is between 2000 to 4000, it is a transition, and above 4000 is a turbulent flow. So you see, basically from laminar to turbulent, there is not a direct flow will directly move from laminar to turbulent, but there will be a transition phase where for some portion Laminar will dominate with some portion, turbulent will dominate, and after a certain rise in velocity, it will be fully developed into turbulent flow. Now, flow between two parallel plate. If Reynolds number is less than 1000, then it is a laminar flow. Between 1000 to 2000, it is a transition phase, and greater than 2000, it is a turbulent flow. For wide open channel, it is less than 500 laminar, 500 to 1000 it is turbulent, sorry, transition phase, and for greater than 1000 it is a turbulent flow. Now we come to see detail about laminar flow. A laminar flow is one in which fluid move in the form of layers without any intermixing. There is no any intermixing between the fluid particle. It is moving in a layer by layer form. In this type of flow, the viscous force dominate the inertia force. So we have seen here Reynolds number, which is defined as inertia force by viscous force. So if viscous force is more, so Reynolds number will be less. Hence, viscous force dominates in this type of flow. As a result, we have a layer by layer flow. Laminar flow occur at low velocity and low Reynolds number. Example, flow of blood in vein. So flow of blood in a vein is a laminar flow. Now, here we will see laminar flow through pipes. For Reynolds number, if Reynolds number is less than 2000, we have a laminar flow. So now we will see a specific condition of flow through pipe. As the fluid enters the pipe, the particle in the contact with the wall of the pipe comes into rest due to no slip condition. To make up the velocity reduction at the wall, the velocity at the center line keeps on increasing, and until the flow is fully developed as the flow rate is constant. So we have a boundary layer near the wall of the pipe. The center line of the velocity keep on increasing until we have a fully developed flow. It is represented here in the figure. Here fluid enter, and the fluid which comes directly to contact with the wall, it acquires zero velocity due to no slip condition, and gradually the velocity keeps on increasing till it becomes fully developed, and the length which it takes to fully develop the flow is called the hydrodynamic entrance length. The center line velocity keeps on increasing until we have a fully developed flow. The thickness of this boundary layer increases in the flow direction until the flow becomes fully developed and merges at the pipe center and thus fill the entire pipe. The reason from the pipe inlet to the point at which the velocity profile is fully developed is hydrodynamic entrance region, and the length of this region is called the hydrodynamic entrance length. Velocity profile developed in laminar flow through pipe is shown here. So I have explained this. The region beyond the entrance region in which the velocity profile is fully developed and unchanged is called the hydrodynamic fully developed region, and beyond this entrance region we have a hydrodynamic fully developed region. Now velocity distribution. So velocity distribution of pipe flow in radial direction for fully developed region is given as, so in the velocity in this radial direction along the radius is given as, velocity is function of r, so it is given as minus r square by 4 mu, change in drop in pressure along the flow direction, which is the x direction, into 1 minus r square upon r square, where r is the distance from the wall of the pipe and capital R is the radius of the pipe. So we see when r equal to del P by del X is the pressure drop per unit length in direction of flow. R and mu is the radius of pipe and coefficient of dynamic viscosity. So all the terms are constant except this R. So velocity is a function of a radial distance. The maximum velocity as the center of the pipeline and is given as, when we will keep R small r equal to capital R, so this term will get cancelled and it will become r square by 4 mu into del P by del X. Now for average velocity equal to u max by 2, where you average the average velocity of flow in the pipe. So now in the pipe we have shown here the velocity profile for fully developed velocity profile. And this is a shear stress distribution because near the wall the shear stress will be maximum, and as gradually you move toward the center the shear force becomes zero because the viscous effect, which is the main reason for the shear stress, become less. Velocity and shear distribution of laminar flow in a pipe is shown here. Point where local velocity equal to the average velocity is r, at radius at which the local velocity is equal to average velocity is given by capital R upon root 2. Shear stress distribution in pipe flow. So it is a linear relation which is equal to minus R by 4 mu del P, but less because as we move away from the wall, the velocity stress keeps on decreasing because the viscous effect is more dominant near the wall. So this is all for laminar and viscous flow.